Now in this next example, you'll be told to locate the stationary points of the function. The function of x are going to be equal to x squared plus xy plus y squared, and you state their nature, isn't it? So we say for you to locate a stationary point and state the nature, you have to get all the 6 partial derivatives. When we have 2 variables, then we will end up with the 6 partial derivatives, isn't it? So the first one will be, we are differentiating the function partially with respect to x. So if we are differentiating the function partially with respect to x, we denote it as subscript. The subscript denotes the variable you are differentiating partially with respect to. If you put a prime, that is now an ordinary derivative. You see that? So we are differentiating this function partially with respect to x, implying that only x is a variable. Anything else is now treated as a constant when you are doing it with respect to x. Are you seeing that? Anything else is treated as a constant. Only x is the variable. So our function is x squared plus xy plus y squared. So when we are doing it partially with respect to x, only x is a variable. Anything else which is not x is a constant. Are you seeing that? So it means when you differentiate x squared, you get 2x, because x is a variable, in that we are doing it with respect to x partially. Are you seeing that? If you go here, if you differentiate xy, it means y is a constant, because we are dealing with partially with respect to x. So if y is a constant, it means only this x we are differentiating. Then we multiply with the constant, isn't it? So if you differentiate x, you get 1, isn't it? 1 times y. So we have plus 1. Then y squared, there is no x here, meaning the whole of that term is a constant, isn't it? So if you differentiate a constant, you get 0. So after doing this, out of this partial derivative, we can get 2 more. So we can deal with this. We get some 2 more. The first one, here, for the first time we've done it with respect to x. Now we want to do it for the second time again with respect to x. So we have f of xx. We say that is the short form of, if you differentiate f partially with respect to x, if your function was z, was a function of f of xy, meaning differentiating partially with respect to x is just like saying partial z over partial x, isn't it? This is the short form, isn't it? So that the moment if you're doing it for the second time again partially with respect to x, meaning you are differentiating partially with respect to x again, then what are you differentiating? What you already have there, isn't it? So that we already have this, and this is now what we are differentiating again partially with respect to x. Then in the end, we end up with d squared z over the partial x squared like that, isn't it? So this is the short form of that. Are we together? So when we are now doing it again for the second time partially with respect to x, only x is a variable, anything else is a constant, isn't it? Meaning if you differentiate 2x, you remain with 2. Only x is a variable, meaning if you differentiate y, you get 0 because y is not constant, isn't it? You are done with that. Then you go again, the first time you did it partially with respect to x, the second time now you want to do it with respect to y. Do you see that? So we now want to differentiate this for the second time with respect to y. So it means only y is a variable, isn't it? So anywhere you see y with this partial differentiation, that is the only variable, anything else is a constant. So it means this term, there is no y. So it means the whole of this term is a constant because we are now doing it with respect to y, isn't it? So if you differentiate a constant, you get 0. Then if you differentiate y now, you get 1 because we are doing it with respect to y. Only y is the variable. Good. So after that, that is now the first case when we started partially with respect to x. Now we want to differentiate this function partially for the first time with respect to y. This case we did it for the first time with respect to x. Now what about if we do it for the first time with respect to y? What do we end up with, isn't it? Now we now want to differentiate this function for the first time partially with respect to y. So if we are doing it partially with respect to y, it implies only y is the variable, isn't it? X is now treated as a constant. Are we together there? So it means if you come to this term x squared, there is no y here. So it means this all of this term is a constant. In that we are doing it partially with respect to y, isn't it? So the whole of this is a constant, and if you differentiate a constant, you get 0. Then in this term, we are doing it partially with respect to y, meaning this x is now a constant, isn't it? So if you differentiate y, you get 1. So you remain with x. That constant times 1. Then if you differentiate y squared partially with respect to y, meaning y is a variable, you get 2y. And you've done that. So for the first time, you've done it with respect to y. For the second time, if the first time here is with respect to y, for the second time we want to do it partially with respect to y again, isn't it? So if you do it partially with respect to y again, it means only y is a variable. So this term here, there's no y, so it is a constant. If you differentiate a constant, you get 0, isn't it? Then if you differentiate 2y with respect to y is a variable, you remain with the 2, isn't it? You go to the next one. The first time, you did it with respect to y. Then the second time, now instead of doing it with respect to y again, we now want to do it with respect to, partially with respect to x, isn't it? So if we are differentiating this partially with respect to x, what? Only x is the variable. So anywhere you see x, that is the only thing you can differentiate. Anything else is a constant, isn't it? So here, if you differentiate this x partially with respect to x, you get, in this term, there is no x, which means the whole of this term is a constant, isn't it? And if you're differentiating a constant, what do you get? 0. So it means this derivative is always the same as this, isn't it? And you can see this one means you did it, you differentiated twice. So first time partially with respect to x, second time with respect to y. First time partially with respect to x, second time partially with respect to y. And you can see it is always the same as if you differentiate it first time with respect to y, and then second time with respect to x, meaning this derivative is always the same as that, isn't it? So, from that, we've now found the 4 partial derivatives. So, having found the 4 partial derivatives, what you know is that at the stationary point, the derivative of the curve is 0. So, you know that at the stationary point, the derivative is 0. And here, because we have partial derivative, we are doing partial differentiation, meaning we have more than one derivative, isn't it? So we have these 2 derivatives. Are you seeing that? So if the derivative is 0, it implies it is either this first derivative, partially with respect to x, which is 0, or this derivative partially with respect to y, which is 0. So it means we are going to form simultaneous equations, isn't it? So when we solve the simultaneous equations, we will be able to identify, to determine that given stationary point, isn't it? So here, if you substitute your this derivative you found to be 2x plus y, it has to be equals to 0 for you to determine that stationary point. This derivative you found was x plus 2y, it is equals to 0. So if you solve this simultaneous equation, you will be able to determine that stationary point. So in this case, you can see it is a single stationary point in that the equations are linear, isn't it? When you have linear equation, it means you are going to get one solution, isn't it? So if maybe one of the equations was not linear, was quadratic, then you are sure you will get more than, you will get 2 equations if it is a case of quadratic, isn't it? Good. So here, you use any method you feel comfortable with, substitution or elimination. Like from this first equation here, if you make y the subject of the equation, you can get y is equals to negative 2x, isn't it? If you take 2x the other side, isn't it? So that you use this from first equation, you substitute in the second equation, isn't it? So in the first equation here, we found y to be negative 2x. So where there is y in the second equation, we put negative 2x, isn't it? So what do we get? We get x plus 2y is equals to 0. Because x plus 2y, meaning where there is y, we put the value of y from first equation, which we found to be negative 2x, isn't it? So if you solve this equation, what will you get to be the value of x? So automatically you will see x is 0, isn't it? Yes. X is 0 in that case. So x, this implies that x is equals to 0. So when x is equals to 0, what is y? See, where there is x equals 0, because y was negative 2x, meaning y is also 0. So you know a point is in the form xy. So it means that stationary point is the point 0. Are you seeing that? You determine that stationary point. Once you found the x value, you substitute it in the other equation to get the corresponding y value so that you have your coordinates, isn't it? So this is the stationary point you are looking for. The stationary point here is the point 0, 0. Are we together? Now, having determined that stationary point, we've located the given stationary point. Now we want to state its nature. So to state the nature of this stationary point, you have to use the discriminant. And we found from the last lesson, we actually saw that the determinant of the Hessian matrix is actually the same as negative discriminant. All discriminant is the same as the negative of the determinant of the Hessian matrix. Meaning, if you are going to construct an Hessian matrix of this function f of xy, if you are constructing an Hessian matrix, it is a matrix of second order partial derivatives, and the second order partial derivatives, the elements are constant. Meaning, if you don't get a constant, you substitute the values of those given stationary points, isn't it? So if you look at this, when we now want to get, when I put these strokes, meaning I'm looking for the determinant, isn't it, of a matrix, because I have two variables here in the function f of xy. If there are two variables, meaning it is a 2 by 2 matrix, because the Hessian matrix has to be a square matrix, isn't it? So if we have two variables, x and y, meaning it is a 2 by 2 matrix, isn't it? So in a 2 by 2 matrix implies we have 4 elements. So you put your 4 elements, then you start following the order of a matrix. The first element forms, because when you are defining the elements of a matrix, you start with the row followed by a column, isn't it? Meaning you define the row first. So the first element here is x. So it means x forms the first row, the horizontal arrangement. That is the first row. We are done with the first row, isn't it? Then y is the second element, is the second variable here, so y forms the second row. So you define the second row. Row first. Row 1 is x, row 2 is y. You are done with the row. Are you seeing that? Then you now go to the column after row, isn't it? And when you are doing the column 1 comes first, and column 1 takes the first variable, isn't it? So it means column 1 is x. So this is column 1. So column 1 is x. You are done with column 1. Are you seeing that? And column 2 is y. So that is column 2 is y. So are you seeing? You constructed the Hessian matrix. So we are now looking for the determinant. Those strokes means determinant. We will not put it in form of a matrix. No, the determinant is what we are interested in, isn't it? So if you look at this, you will see that the determinant here is the product of the elements in the main diagonal, f of xx, f of yy minus f of xy times f of yx, isn't it? So that if you expand this in full, if you expand this, you will end up with meaning you differentiated this twice, successive differentiation, partially with respect to x, partially with respect to x, isn't it? Meaning this in full is the same as if you say this function f of x, if it was z to be this function, meaning you differentiated z successively with respect to x twice, isn't it? Then this one means you differentiated that z twice, meaning it is y squared yy, isn't it? So it means it is this times that. Then it is minus this times this. And we've seen this is always the same as this, isn't it? So it is just like this squared. Because this is always equal to this, this value is always the same as this, isn't it? So it is just like f of xy squared. Are you seeing that? So f of xy, meaning the first time you differentiated it with respect to z, the second time with respect to y, because it is the same as this, meaning it is like it is squared. So are you seeing? This is the determinant of the Hessian, this is the determinant of the Hessian matrix, but the discriminant is always starting with that, isn't it? So if you look for the discriminant, it is partial squared z, partial x, partial y minus partial squared z over partial x squared, partial squared z over partial y squared. So you can see, for you to get this, it means it is you multiply this determinant of this and matrix by negative, isn't it? Are you seeing that? So it means the discriminant So from here you can now see the discriminant is the negative of the determinant of the Hessian matrix. So the moment you get the determinant of the Hessian matrix to be 4, then it means the discriminant is -4, because the discriminant is the negative of that, isn't it? So it means the moment the determinant of the Hessian matrix is greater than 0, then the discriminant is less than 0. See what it implies? It is the opposite of the other. So, having constructed this, we now go straight and we substitute our point. So we have our point is 0, 0. So let us get that Hessian matrix. So start substituting for this point. What is f of x, x? Go and check. You found it to be 2. You put it where it is supposed to be. If it was maybe 2x, then you substitute the value of x of this point we're dealing with, isn't it? To make it a constant, isn't it? Then the next one, f of xy, you found to be, you substitute it where it is supposed to be. Then this value here, f of yx, you found it to be, you put it where it's supposed to be, isn't it? Then this last element, f of yy, you found it to be, you put it there. So what is that determinant? Multiply that. Product of the elements in the main diagonal minus product of the elements in the other diagonal. What do you have? 3. That is 2 times 2 is 4. Minus 1 times 1, isn't it? You get 3. So what does that mean? It implies that the determinant of the Hessian matrix is greater than 0, because 3 is greater than 0, isn't it? So if this is greater than 0, then that simply implies that the discriminant is less than 0, because the discriminant is negative, the determinant of the Hessian matrix, isn't it? Are you seeing that? So when the discriminant is less than 0, then automatically that is a turning point. When the discriminant is less than 0, it is a turning point. Or when the determinant of the Hessian matrix is greater than 0, then it is a turning point. Then when the discriminant is greater than 0, it is a shadow point. And the moment when the discriminant is greater than 0, it implies that the determinant of the Hessian matrix was less than 0, isn't it? Are you seeing that? So from here, after you've identified that your point 0, 0 is a turning point is either a minimum point or a maximum point, isn't it? So for you to get the minimum point or the maximum point, you use the first principal minimum. From the square matrix was a 2 by 2 matrix. The first principal minimum is the square matrix on top of it, 1 by 1 matrix. And the 1 by 1 matrix element you can extract there is the determinant of f of xx. It is the one forming 1 by 1 here, isn't it? So it means the f of xx forms the first principal minimum. So what is the value of f of xx? 2. So that is 2. So if it was not a constant, if it was maybe 2x, then you substitute the value of x of that given point you are dealing with, isn't it? So f of xx is 2. So 2 is greater than 0. Are you seeing that? When the first principal minimum is greater than 0, then it is a minimum. It is a minimum. So you say we found the first principal minimum is greater than 0, then it implies this our point we are dealing with, point 0, 0, is a minimum point. It is a minimum point. Remember, when f of xx is less than 0, then it is a maximum point. It's always the opposite, isn't it? When f of xx is less than 0, it is a maximum point. But when f of xx is greater than 0, then it is a minimum point. Are you seeing that? So once you've located the stationary point, when you are determining the nature of a stationary point, you construct the Hessian matrix. And when you know when the Hessian matrix is greater than 0, then automatically the discriminant is less than 0, isn't it? So when the discriminant is less than 0, it is a turning point. When the discriminant is greater than 0, it is a shadow point, isn't it? And when you find that it is a turning point, you have to show whether that turning point is a maximum point or a minimum point, isn't it? You see that? And it is a minimum point when the second principal minimum is greater than 0. And it is a maximum point when the second principal minimum is less than 0. So that is how to handle such kind of problem.